Yeah, so welcome back. I wanted to talk about this this section we skipped once a little back. It's in section 3.8 of our book. It's called Newton's method. It's a cool little topic that we skipped. I'll just tell you what I think it is. I think it's a I want to call it a numerical procedure we can adapt it and use it for several things, but I'm going to say to start off that it's for finding an x-intercept, for finding an x-intercept of a function. I mean, do you have and again, I use this word numerical procedure as opposed to an analytic procedure. Maybe you know the difference in those words. Maybe I have to remind you, but do you know it? So let's say I wanted to find the x-intercept of this function. And guess what? You don't need Newton's method. You guys can find the x-intercept of this function. How do you find an x-intercept? Set it equal to 0, set y equal to 0, and solve for x. You actually get two x-intercepts. What are they? Move the 2 over. Plus and minus the square root of 2. Is that what you guys said? Mm-hmm. Good. And by the way, that's approximately plus or minus 1.414, blah, 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 blah. Actually, can you tell me what that is? What is square root of 2? 414.
213562.
All right, thank you. All right. So if I do this, so why am I going to teach you something that you already know how to do? Well, just bear with me. It's a numerical procedure that I'd like to teach you. It works for things that we can't do. So here's the theory. For a numerical procedure to find an x-intercept. Watch this. It's pretty cool, and it uses a derivative. That's what we've been doing in chapter 4 is using derivatives for things. So this uses a derivative. So if I have a function, I'm just going to be kind of abstract here. I've got a function, and I'm looking for this x-intercept. So here's how this procedure works. You guess. You make a guess. Okay? And hopefully your first guess is kind of close. But you make an initial guess, and that's called x1. And that's your initial guess. Okay? Good job. But you're not quite close enough. So now here's what you do. You plug that x into the function. When you plug that x into the function, you get a y value. I'm going to call it f of x1. That's my x1. That's my f of x1. And I want to create a tangent line at that point. So if I want a tangent line at that point, I think I'll need the slope of the tangent line, which means I'd probably need a derivative. Thank you very much. So the derivative of this function, I'll find the derivative of this function, and then I'll evaluate this derivative at that point, right? At that point, I'll get the derivative at that point, and that will be the slope at that point. Okay, cool. So if I have a slope and a point, then I think I can maybe get the equation of a tangent line. And by the way, here's the game. The game is that the tangent line so I want to find this tangent line. And then the game is I'll try to find the x-intercept of the tangent line. Because remember, I'm trying to find the x-intercept of the function, but for some reason I can't, I guess. So what I'll do is I'll find the x-intercept of the tangent line, which, if you can look at it, it looks pretty close. Might be close. I mean, that is kind of the big theme of calculus, is that the tangent line acts like the function right around that point. So anyway, but it won't be perfect. It won't be perfect. So the x-intercept of the tangent line won't quite be right, but it'll be better. You know what I'll do with that x-intercept of the tangent line? I'll use it as my second guess. And so I'll call it x2. I'll plug it into the function, get a new point, find the derivative at that point, create a new tangent line. Find find the x-intercept of that new tangent line. That's not too bad, but it's still not quite good enough for me. So then I'll do this process again. See, Newton's method is this process, and then you repeat it over and over and over again. Well, let's just back up here a second. So, well, hang on, one more time. So this next one was x3, I guess. Now, what was the process? The process is you get this point, you plug it in the function, you get a y value, you find the derivative at that point, you create a tangent line at that point, and the x-intercept of the tangent line should be close to the x-intercept of the function. And it really gets pretty close after 3 or 4 steps. It doesn't take too many, it doesn't take 9 or 10 steps, but after 2 or 3 or 4 steps, it's pretty darn good. Now, let's talk that through here a second. What did I do? I started with a point, x1. Did I find a y value, f of x1? And so this really was a point. I had an initial guess. I found a y value. I found the slope. What was the slope? F prime of x1. That was my slope. Okay, can you get a tangent line then? You know how to do the equation of a tangent line. You y minus the y value. I'm doing the point slope form. Y minus the y value equals the slope at that point times x minus the x value. Yeah, this is sort of the equation of the tangent line. All right, so I had an initial guess. I plug it in the function. I get a point. I find the slope at that point. I create a tangent line at that point. And then what was the next step? Do you remember after I create this tangent line, then I look for the x-intercept of the tangent line. Right. Now how do you find the x-intercept of this tangent line? You let y equal 0, just like you find the x-intercept of anything. You let y equal 0 and solve for x. Okay, because keep in mind, the x1 and all that, those are numbers, although they're abstract in this case. But you're saying to find the x-intercept of this guy, I'm going to let y equal 0, and I'm going to solve for that x. The actual x. Okay, cool. How do I do that? Okay, so this is a 0. All right, this is a 0. This y is a 0. This is negative f of x1. This is f prime of x1. I mean, I'm proving this theorem to you. I'm proving this Newton's method to you. But it's not difficult. You're following me, aren't you? It's just a tangent line. Now I'm solving for x. So what should I do? Maybe, algebra. Maybe divide by this. I think I'll divide by this f prime here. So I got this negative f of x1, that's the y value, over f prime of x1. That equals x minus x1. Remember, I'm trying to solve for x. So one more step, I think. One more step. Add the x1 over here. Let me see here. I need a little room. If I add the x1 over there, I get x equals, now I'm writing it different, sorry about that. What did I do? I just added the x1 over there. So x1 minus this is x. And then I wrote it backwards, sorry, I wrote it. You okay with me? X equals x1 minus this, x1 minus this, cool. And that's my new x-intercept, for the first tangent line. And then, do you remember what I called that? I called it x2. And then you know what I did with that x2? I played that same game over again. In other words, we call this x2. And then, you know what I did? I took x2 and plugged it in this formula. Of course, I didn't have a formula a few minutes ago, but now I got myself a formula. This is Newton's method formula. And now, you take the x2 that you got as your answer to the first. And when you do this once, it's called one iteration. So I just did one iteration of Newton's method, and it produced this x2. Now what do? Feed it back into the formula. So I feed x2 back in there, right there, right there, right there, and it spits out x3. And then I feed x3 back in there, and it spits out x4. And each one of these should be getting closer and closer to the actual x-intercept. It's a numerical procedure. After several iterations, that's the word, after several iterations of this numerical procedure, we narrow in, we get closer and closer to the actual x-intercept. So in general, this is, like I said, I could write the next step is you get x3 by plugging in x2. I mean, this is, I just described that. I don't know if I really want to write it. What I really like to write is, here, let me move up here. In general, what you say for Newton's method is to get the next x, xn plus 1, you plug in the previous x, which is xn, and you plug it into this formula. How are you guys doing? You guys okay with that? Mm-hmm. Again, if you're plugging in x1, it's spitting out x2. If you're plugging in x2, it spits out x3. And you feed it back in, and it's a numerical procedure. I mean, you can sort of, I don't know what kind of programming experience you might have, but you can see how this is, you program this into a computer. Might be the best way to do this. Even a simple Excel program, or maybe even a little program on your calculator. I don't know, again, what kind of programming skills you have. I'm not going to teach you programming skills. I don't know too many myself. But in some future programming class, somebody may say, hey, let's write a program for Newton's method. And you won't be experts on it, but you have heard it once. And you can look it back up and watch it, or whatever you want to do. I mean, this is the procedure. Let's try this procedure. Let's try it for, like I said, let's try it for this function. So I want to find the x-intercept of this function. Well, hang on, I did it. the real way, the analytic way, we found this x-intercept. But let's see how good Newton's method does. Let's see how it works. So if I want to do Newton's method, I'll get rid of this stuff. I guess one thing I need is a function, so I guess I got my function. There's my function. The other thing I need is, well, here, let me just write it over here. I need my function. I need my derivative of my function, I guess. What's my derivative?
2x.
Thank you, 2x. And I think the other thing is I need an initial guess. I need an initial guess. And so, I don't know. I guess I'm using some previous knowledge to, I mean, I know the answer. So I can make a reasonable initial guess. What would you guess? 1. 1 would be good. 1's good. 1.5 would be a better initial guess, but let's pretend we're not that smart. We'll try 1. So my initial guess is 1. All right, then here's my game. I played that game. Let's see what happens. To get x2, I have to plug in the initial guess, the initial x, that's a 1, minus f of 1 all over f prime of 1. All right, well what is that? Let's work on that a second. That's f of 1 means plug 1 into the function. Plugging 1 into the function is 1 minus 2. I guess that's negative 1 over f prime of 1 is plugging 1 into the derivative, which is a 2. Oh, guess what that is? 1.5. Should have used that for my initial guess. Anyway, my initial guess was 1, and now my x2 is a 1.5, which is getting closer to the actual answer. But let's try it again, see if it gets even closer. Let's feed it back in and get an x3. Here we go. To get x3, I plug in the x2. 1.5 minus f of 1.5, which is 1.5 squared minus 2. I think that's a 0.25. All over 1.5 times 2, which is a 3. Help me, please. That's a little decimal. You're going to subtract it from 1.5. What is this x3?
112.
Oh, and you okay, and subtract it and decimalize it.
1.416666.
Okay, thank you. Damn, that's pretty cool, you guys. That's getting close. Let's feed this in. Now the problem is, what should I feed in? A 1.41666. How many damn sixes should I write? The more you write, the better your next guess will be. I mean, the more you round it off, the worse your next guess will be. But the more you, so I'm going to try, I don't know, let me try a 1.4166. I'll put 3 6s in there. Actually, and then the fourth one will be a 7. Is that okay with you? I rounded it. 6, 6, 6, 6, and around. So I rounded it. And then I got to plug that into my function. Wow. So that's going to be a 1.416667 squared minus 2. That's the function over 2 times 1.416667. Again, is this kind of a pain to do this on your calculator? It would be kind of cool if there was a program written to do this. It'd be easy to tell the program, to tell the computer, take your answer and feed it back in, please. Take your answer and feed it back in, please. And you just hit enter, hit enter, hit enter, and you know, be a little easier with a little program. That's really the idea. But we're doing it without a program. We're cranking it out. Bless you. Bless you, bless you.
Thank you.
So what do you think? Can you help me with this one? Using my decimals, using my rounding, can you give me, I don't want to do it again. I think this will be my last attempt here.
1.41422.
Really? 1.41422. Damn, that's pretty good. Good, I don't know, I might be happy. What's the real answer? Remember the real answer? 1.41213. Wow.
That's round.
And you rounded this a little bit. Yeah, okay. I don't know, I'm happy. How many times did I do Newton's method? 3? I plugged in x1 and it spits out x2. Then I got x3, then I got x4. You're right, I did 3 iterations of Newton's method, and it worked pretty good. I don't know. I think it's interesting. I think it's cool. Like I said, someday you might have to write a program for it. I'm kind of done with this topic, except I want to try one more problem that you really can't do by hand. There's a problem in the book. It wants to know. It wants to know when this function, f of x, is 2 minus x squared, which looks a lot like what I just had, and then this other function, e to the x over 2, and they want to know, where does it intersect? Where do they intersect? And you might say to yourself, wait a minute, Newton's method is for finding, what's Newton's method good for? It's a numerical procedure for finding an x-intercept of a function. Nobody said it was good for finding point of intersection. But can your brain adapt? Can you change this problem? I mean, what do you do when somebody says find a point of intersection? What do you do when somebody says find a point of intersection? Set them equal to each other. You're right. You set them equal to each other. And by the way, this is totally unsolvable. You cannot solve this analytically. You cannot, there is no, you can't take the log of both sides. You can't square root. There's no way to get x by itself here analytically. So I need a piece of technology or a numerical procedure for this. But right now it's setting them equal to each other. I wish I could adapt it into a x-intercept kind of problem. You know, an x-intercept kind of problem is when it equals 0, when something equals 0. Can you, what would you do? Subtract somebody, or yeah, and as a matter of fact, let's subtract the other crap. Let's move this x squared over here. It's an added x squared and it's a negative 2. you know, when you set something equal to each other, then the very next step is you move everybody to one side and it does equal 0. And so then if you kind of thought of this as a function, maybe I shouldn't call it f or g because that's f and g. Maybe I'll call this h of x. But if I thought of this as its own function now, the question is, when does this equal 0? So the question, when do these two functions intersect, turns into the question, when does this function equal 0? Okay, cool. Well, then I could use Newton's method on this dude. Let's try it. That's my function. What is, I need h prime. I need h prime of x. The derivative, please. With a half, spit out a half. Good. 1/2 e to the x over 2 plus 2x. That's the derivative. Okay. That's the derivative. I need an initial guess. I got my derivative. I got my function. I need an initial guess. What's nice, I grabbed this problem out of the book. The book had a little picture of this for me. You could use graphic calculator and get a picture, but I can just help you quick. Or you could do some estimating, and you could do some actual guessing to see what it would be. But the book had this picture. That's a parabola up 2, upside down parabola. That's an e function, kind of like this. And so actually there is a couple points of intersection. And there looked like, the book had a picture, and according to the book's picture, it looked like it was close to 1. So I think my initial guess, well, it depends which one I'm looking for. But if I'm looking for this point of intersection, then my initial guess would be 1. I think this other one would be -1. Yeah, you can't really look for both at the same time. You're looking for one at a time. And you're going to do a numerical procedure. So let's try it. My initial guess is x1 equals 1. And here I go. In order to get x2, I'm doing Newton's method. Newton's method says you plug in your initial guess right there. And then you plug your initial guess into your function divided by your initial guess plugged into your derivative. Okay, Jesus. That's e to the 1/2 when I plug in a 1. Plus 1 minus 2. That's me plugging 1 into the function. You guys okay? And now I'll plug 1 into the derivative. That's 1/2 e to the 1 over 2 plus 2. You know, in order to decimalize this and figure this out, I do still pick up a calculator and decimalize all this crap, you know? And maybe you could help me. I forgot my calculator. Conveniently, forgot my calculator today. Can you help me spit out a decimal here? This is a decimal divided by a decimal. When you're done, please subtract it from 1.
Got -0.893469.
Really?
You got error.
Really? Wait a minute. So you got to do e to the 1/2.
That's
Square root of e. 2 minus 1. That's a -1. Plus 2. You got to divide that. After you divide it, subtract it from 1.
I got 0.2297. Oh wait, there's a 1. 0.7702. Yeah.
I got 0.770312.
770312.
168.
All right, I'm gonna take this. Hey, I think I like that. Some of you were shouting out some numbers I don't like. By the way, I'm kind of remembering. I remember I know the answer because I knew it was close to 1. So listen, I didn't want the second guess. So my first guess was a 1. some of you were telling me that this was negative. See, that would have been kind of bad. If my first guess is a 1 and then my next guess is way over here, you know, it should kind of be narrow. It should be close in here, I think. There are places where Newton's method fails, though, where the tangent line shoots it off to it doesn't work that well sometimes. Anyway, you want to try plugging this in? It's kind of a pain. What am I doing? Plugging in a, oh my God, a 0.7703 divided by 2, right, you guys? Plus a 0.7703 squared minus 2 all over 1/2 e to the 0.7703 over 2 plus 2 times, I mean, this is a pain. You don't like this now, do you? You just quit liking it. You thought it was cool until now. I got you. I agree with you. You need a program. You need to write a little program. Then you don't have to type in all these damn decimals. So, if anybody ever finishes this, you have x3, which I hope is a better prediction of the answer. We might have to wait a couple hours.
No, I don't think it's right.
I have 0.5630.
0.5630?
38.
38? I don't know about that. See, I keep looking at this picture, and the answer should be about 0.8, 0.9, I think, 0.7. And I don't want it to be negative.
0.7425.
0.7425? You actually did all this work.
I had X, and then I plugged them.
Yeah, good. Yeah, there's a way to.
So I just do that.
You can hit entry, right? If you have this in your calculator, there's a way to play with your calculator and kind of feed it back in. There's a way to sort of program your calculator or play with your calculator. But anyway, I think I'm going to trust him. I'm not sure.
Yeah, I got the same idea.
Yeah, me too.
Okay, good. Now I'll trust him. I'll trust you 3 or 4. Okay, I am totally trusting you, which is scary for me. But I'm not in control. Anyway, that's it. No big deal. Little lecture on Newton's method. Let's quit that.